Example 6, a spotlight on the ground shines on a wall 12 meters away. So let's start off with that. So there's the floor, there's the wall, and here's the spotlight. And it says a spotlight on the ground, so the spotlight's on the ground there, you can see that. Shines on a wall 12 meters away. And the way light works is it goes kind of outward like that. We're not talking about a laser here, we're talking about like an incandescent light. So it kind of goes out there, makes this circle there on the wall. All right. A man 1.9 meters tall walks from the spotlight toward the building at 1.2 meters per second. How fast is the length of his shadow decreasing when he's 5 meters from the building? So, if the man is here, all right, and he's 1.9 meters tall, right? Notice I put 1.9 meters there because the man's not going to be shrinking or growing as he walks. He's just walking. He's as tall as he is. Okay, that's not a changing measure, right? Now, as he walks towards the wall, his shadow is going to be projected on the wall to here, right? The light might go up a little higher, but this part of the light here would create a shadow. So this shadow is going to be changing as he moves. If he gets closer to the light, the shadow is going to go higher. If he gets further from the light, the shadow is going to get lower. Because again, the shadow is based on his position in relation to the light. So if he moves here, for example, now the light's going to be creating a shadow like that. So as he gets closer to the wall, you can see his shadow should be shrinking. And again, won't worry about which direction he's going. The other thing's happening is he's walking from the spotlight towards the building. So he's going this way, right? All right. So this or this, the distance he is from the spotlight or the distance he is from the wall is changing. Take your pick. Doesn't matter which one you go with. I'm going to go with this as x here. X is the distance. Let me highlight that with some different colors. So this right here is x. All right. Can we determine how big this is here?
12 minus x.
It's 12 minus x because we know for a fact the entire distance from the spotlight to the wall is 12 meters away. So this distance here is 12 meters. The wall isn't moving, the spotlight isn't moving, so 12 meters is 12 meters. But x and 12 minus x are changing, so we're using variables to represent the green and the red there. Again, the shadow is changing height depending on which direction he's going, right? So that's a valid picture for what's going on. Now we're going to assume the man is standing at a right angle to the floor and the wall is at a right angle to the floor. We can make some assumptions like that. So what we're looking at here, this picture is overlapping right triangles. And we're looking for a relationship between the distance the man is from the spotlight and the height of his shadow. So, see if you guys agree with this. If I did x and 1.9 on top, x and 1.9 come from the small right triangle here. The big right triangle has 12 and s as corresponding pieces. 1.9 corresponds to s, and x corresponds to 12. Everybody agree that that equation is valid?
Yes.
It relates the variables x and s, x being the distance the man is from the spotlight, s being the distance the man is from, or the height of the shadow of the man. And that's a fine relating equation, there's nothing wrong with it. If I did use that equation, I'd probably want to make it 1.9 s to the negative first power, create a power structure out of it. 1/12x is fine the way it is. All right. Now, if we start getting some more specifics here, the other stuff I need is my x equals and my s equals and my dx over dt equals and my ds over dt equals. And this is where I start getting specific information about x and s and all this other stuff. Now, it says he walks from the spotlight toward the building at 1.2 meters per second. So which direction is he going?
Towards the building.
Towards the building. So the building's here, he's going this direction, right? Looking at the dimension x in the picture, is x getting bigger or smaller?
X is getting bigger.
X is getting bigger. So this 1.2 meters per second is going to be a positive 1.2 meters per second. All right? And the question asks us very specifically, how fast is his shadow decreases? We're looking for ds over dt when he is 5 meters from the building. Okay, 5 meters from the building, that means that this right here is 5, right?
Uh-huh.
So what does x equal? Very good, 7. Be very careful, depending on where you put letters. If I put x right here, x would equal 5, this would be a 12 minus x, that's 12 minus x now, different equation and stuff like that. So once you've set in stone what your picture looks like, and you've established what things are in your picture, you have to put the correct values of things based on what picture you've drawn. And again, there's no, like, this isn't the best picture or the worst picture, it's a picture that works. Alright, so based on the picture I drew, x equals 7. If you put x here and 12 minus x there, x is going to be 5, but this is going to say 12 minus x instead of x. Alright? S, we have to determine from what x equals, right? And if you take a look, my relating equation here can tell me what s equals. Do I have to do that right away?
No.
Not necessarily. Maybe s sticks around, then it's important. If it doesn't, then it's not. Okay, so I would hang on to that as long as I have everything I have. Okay, and I've got a relating equation, I can go ahead and differentiate and go with that and see what happens. All right. As far as the differentiating equation I'm going to be using, I'm going to put 1/12 x equals 1.9 s to the negative first power. That's how I'm going to write it. Really enforcing the fact that x is being multiplied by just a number, and s to the negative first is being multiplied by a number. They're both power structures, so the derivative of 1/12 x is going to be 1/12 and then dx over dt. And the derivative of 1.9 s to the negative first is negative 1.9 s to the negative second. Right?
Mm-hmm.
Power times coefficient, power by 1, and that's not t, so we're going to put times ds over dt. And notice that s did stick around, so actually finding the value of s is necessary. So to do that, I would just change this x to a 7. So if I take that proportion and I put 7 over 12 equals 1.9 over s, that gives me 7s is equal to 12 plus 22.8 maybe? Let's verify that. 1.9 times 12 is, yep, 22.8, perfect. Okay. Now if we divide that by 7, that's not an easy division, divided by 7, 3.2571, let's go 4 decimal places. 3.2571. Alright. So now I know what s equals. I don't even have to know what x equals. Alright. X's value influenced s's value though, right?
Yeah.
So that's important. Alright. So at this point, if I just substitute everything in, the one thing I don't know is ds over dt, so it's just a matter of doing that. So I get 1/12 times 1.2 equals negative 1.9 over 3.2571 squared times ds over dt, which we don't know yet. So 1.2 divided by 12 is 0.1, according to my math. Is that what you guys got?
Yep.
0.1. All right, that was easy. Negative 1.9 over 3.2571 squared, that's hard, so let's negative 1.9 divided by 3.2571 squared. That comes out to negative 0.1791. ds over dt. So if we just divide 0.1 by negative 0.1791, we should get our answer, right? So 0.1 divided by negative 0.1791 comes out to 0.56. So ds over dt equals negative 0.56 meters per second. And that goes along with what we kind of figured out with the picture, was if the man is moving towards the building like that, his shadow is shrinking, right? We use the proper signs on these things to create the proper sign on our answer. Okay, the math itself should work itself out the proper sign on this answer. All right, but just keep in mind, that's kind of what you have to do in each of these problems. Use some geometric property to draw a picture that allows you to create some relating equation. And that relating equation is going to help you do the process.